So now we want to connect this to chemistry. If electrons are waves, so what is the shape of electron waves? Do you all know this song, The Shape of You, is like Ed Sheeran or something like that? I don't really know his music, but there was a parody that involves electron waves. So I'm not going to play it for you. I'm definitely not going to sing it for you. But I will make it available if you want to look at it outside of class. But here's the potential. Remember that we have the kinetic energy and the potential energy in that last equation. This is the equation for potential energy between two charges. And by the way, this works for electrons. Like we said, it's Q1, the size of the charges, and divided by some constants and the distance between them. For electrons, what you have is you have really small charges. Both the electron and the proton are equal, so we call them both E. And we just make the electron negative and the proton positive. If you have one proton, Z is 1, and so E equals minus E, and you end up with negative E squared on the top here. If you have like a helium atom, then you have 2 protons, and you have to account for both of them. It's clearly going to be a stronger force because it's going to be more, and it's quantized. Protons themselves are quantized particles with clearly defined masses and numbers. You can't have half a proton. If you do, it basically releases energy, and according to E equals mc squared, which is the basis of atomic energy. Again, no, not in this class. So the thing is, the potential energy, if you do this, if you have E times negative E minus times positive ZE, you end up with negative E squared on the top. Everything else is a positive number or a constant. So therefore, V is negative for the typical electron-proton interaction. Does that make sense? Remember potential energy, and potential energy is the way we usually talk about energy in chemistry, actually. So potential energy is negative if it's attractive, if it's an attractive force. So this is, I want you to see that this is a negative energy, just like what we're used to. Free energies that you've talked about, other kinds of energies. Negative is what's more stable, because those are potential energies that we're calculating. Negative is more a bigger attractive force. All right, so basically we can if we can solve this, we can actually calculate any electron for any atom, but it's just really hard. And so we're going to do it for the hydrogen atom, for the lowest electron. So if you calculate that, and this is where I let them do the magic for us, the math magic. The wave function for a hydrogen atom turns out to be pretty simple. It's e to the negative x. Remember that we talked about e to the negative x slopes down like this. It's divided by a length function to sort of normalize it, but it's essentially e to the minus x. The proton's at 0, and as you get farther out from the proton, you're less likely to find the electron. And that is what the picture is that we started with. So here's the math, and the important thing is, here we have our e to the x. Now, if this is the wave function, when you square the wave function, you actually, the way the constraint works is it ends up being 0 at this end, because you can never exactly tie it down on the proton. But then you end up with a radial distribution with a tiny hole in the middle. But mostly it's right next to, it's within whatever these 2 units are. These are picometer units, I think. Whatever these very small units are, it's very close. At the lowest level, it's very close to the nucleus all the time. It just hangs out around the nucleus. That's where it doesn't have much energy to leave home, basically. Some days you just got to be an electron. You just got to hang out, at home. So if you take this in 1 dimension and you do it in 2 dimensions, you get something like this, and you get a distribution where basically you have the electron just close to the nucleus, and this is the probability of finding it in 2 dimensions, away from the proton at the middle. So this is for the lowest energy of electron. So this is the first energy level. It's like the lowest level of the piano string that we showed you. The particle in the box, remember? It would be like this. Like a wave, actually, as it's hanging down right here, this is kind of like the first level, okay? So we'll call this n equals 1. And the other thing is there are some other numbers that you can apply to electrons. If you work out the physics of how electrons move, there are some other numbers, but they only apply to higher energy levels. So the other numbers, which we'll call L, that's 0. And so this is what the boundary numbers are N, L, and M. N is the first one because the wavelength must not become an infinite. It must be tied down at the ends. So we call this 1, and then when it's got 2 of them, we call that 2. When it's got 3, we call that 3. Now, in one dimension, you only have one principal quantum number, and so you only have N. In 3 dimensions, you have other things that come from the boundary conditions. So there's but the thing is, they are 0 until you put in more energy. Just like N is 0 when you don't have an electron at all. When you have an electron, you get 1 for N, and you have 0 for everything else. Then as you move up, you're able to get higher numbers of N and higher numbers of the other 2. These are 3-dimensional ones. Because the wavelength must match itself at the poles in 3 dimensions, you have a number for that. Because the wavelength must match itself around the equator, you have a number for that. And so we call the second number L, and the third number M sub L, okay? But these are fundamental quantum numbers that just come out of 3D waves. The easy one to understand is N. The main thing about those is that as you're getting in more numbers, you're going to have more nodes. You're going to have weirder shapes. The N equals 1 number gives you basically a circle or a sphere in 3 dimensions. But you're going to get more complicated shapes as you have more complicated numbers, possibilities, and more nodes. So here's what happens when you move up to N equals 2. L still equals 0 for the first one. And so actually, that ends up still being a sphere, just with a little weirdly shaped. You see how it's a sphere, and then it has like a second level where it goes up. So it has it's like a 2-layer sphere. And we call this the 2s level. When we have the L number going up, you actually have a higher energy and a weirder shape. The shape looks like this in 1 dimension. When you square it, it looks like that. And by the way, the square, you can see the the sort of onion type layer for the 2s. But the 2p, notice the 2p is actually farther out than the 2s. It's more over here. You have a little bit of the 2s is farther in. And so the 2p is farther out, and it's definitely farther out than the 1s, right? The 1s is within 2 here, so it's really close. When you add more energy to the electron, it goes farther out from the nucleus. And it can get more waves to it. When you do those in 3 dimensions, actually when you take the 2p and you do it in 2 dimensions, it looks like this. When you do it in 3 dimensions, it looks like the little balloon, the little, do you remember p orbitals? Their shape comes from this equation. And so, here it is. And because you have 3 m sub L numbers for this, for n equals 2, L equals 1, then you can start to get m sub L numbers, which can be either 1, 0, or minus 1, because it's not a sphere anymore. It is this oblong thing. And I think it comes from the fact that it's expressed in 3 dimensions. You have 3 ways to do it. It's like the electrons can go in and out, they can go up and down, or they can go side to side. And it turns out that the way that you can arrange all 3 of these are available to them. Each of these has a different m sub L, and that's how it works out in math. And again, we're getting to the edge of what we can do with math, but I want you to see 3 dimensions equals 3 p orbitals. Isn't that interesting? You know? So the reason why we have 3 p orbitals might be related to the fact that we have 3 dimensions of space. You can put them all together, and so that means you have these orbitals, and each orbital can hold 2 electrons, right? So you can put 2 in the s, 2 in this, 2 in that, 2 in that, and you can have 6 in the p's overall. And that is what you can do with n equals 2, with the second energy level of electrons. And look at that. You have a node. When you have the higher energy p orbital, you have a clearly evident node in 3 dimensions that you can see. It's like you've taken the balloon and you've twisted it. And in fact, that's kind of what you've done. You take the balloon, you put energy into it, and you twist it because it's a wave that has to be twisted, not just cut up, you know. So you have nodes there, there, and there. And on average, the p electrons are farther away from the nucleus. They have more energy. You can say they're moving more, but it's more that they're moving differently, and they're moving farther out. Okay? Moving more is okay in my book. So when we get up to n equals 3, now we have we still have n equals 1 and n equals 3, so we have 3 possibilities for the p orbitals. Then we have actually 5 possibilities for the next one number up. So n we have 1 possibility, the next one we have 3 possibilities, and now we have, I think actually I had a typo, I think this is actually the m sub l, but I'll let myself correct that on a later slide. Whatever it is, the possibilities go up. As you go up, they go up by 1, then there are 3, because you can have 1, negative 1, or 0. And then there are 5, because you can have 2, negative 2, or the 3 in between those. So it's the way the math works out. And so the next possibility for the 3rd level, it opens up 5 possibilities for the d orbitals. On top of at the 3rd level, you still have another set of p's and another single possibility for s. You see how each time you go up, you're opening up new possibilities, and they stack on top of each other like this. So that's why you have, and that's why you have SPD. You probably in chemistry classes have never dealt with f orbitals, okay? Stop me if I'm wrong about that. But I'm pretty sure that f orbitals have never shown up. That's because they're really high energy. If you work with like lanthanides or something like that, then you're going to have like f orbitals. But you might be able to predict, as you go up, they get more complex, more lobes, and more nodes between the lobes. So it looks like they're more stressed because they are more higher energy, you know? They are more complex because they have more energy to create the shapes. And so that's why I say it's like balloon animals, and actually when I describe this in the book, I do use that metaphor of balloon animals. The more energy you have, the more they twist them. You know, every time you put energy, it sort of twists it. And you have 1 possibility, 3 possibilities for p, 5 possibilities for d, and you can follow that pattern, 7 possibilities for f. There actually are orbitals. You can keep adding energy as long as you want. How many possibilities will be in the one beyond f, which is called g, by the way? You want to predict? You'll be right. Yeah, exactly. So it goes 1, 3, 5, 7, 9, and that's the way the math adds on. So realize that this is like the one-dimensional, this is like the 3-dimensional case of the one-dimensional thing that we're dealing with. 1, 3, 5, 7. It's just that once we're getting up to there, f orbitals even, we're just barely starting to get into the f orbitals at the end of the periodic table. So to get to the g orbitals, you have to basically focus a lot of energy on a single atom. You're not going to have a material with a bunch of g orbitals in it. But you can calculate it, or right, we calculated all of these by just plugging in the numbers and going, and I just want to show you, you actually can see exactly what the calculations look like right here. So you look at this, and I just want you to see M, L, and N. And in fact, yeah, I think I did have a typo earlier, because you have the M, L, and M. And remember that M can also be negative. So in a sense, you have other ones, like you have an M equals -1 on this side over here. But they just didn't show it because it's just the exact equal and opposite. So as N goes up, L gets more possibilities, M gets more possibilities, but you end up with 3 possibilities for L, 5 possibilities for M, and then as you go up even more, you end up with 7 possibilities. So here's your prediction. Let's see, we have, here's 5, here's 7, there's there's 9. So that's what it would look like. That's g orbitals. And you can go all the way down. They just said it was ridiculous, but you see how they get more and more twisted as you get more and more energy in them. So yeah, we can calculate what it is, and we can probably do it in isolated ways. So if you want to think, if you like science nerd songs, you can look up the Ed Sheeran parody of The Shape of You, which actually deals with these exact terms. It talks about N, M, and L numbers. But the main thing is, the other thing to remember is that because electrons have opposite spins, which is technically a fourth quantum number called M sub s, the spin's even really weirder than the other ones. But the main thing is each orbital can hold 2 electrons. And so you end up with the 1s orbital. It can hold one electron or 2. And in general, the lowest energy ones fill up first. And so you end up with 2 1s elements. Then you get to lithium, and it's the first one with a 2s. And then beryllium has 2 2s's, and then you end up filling the p's. Within the levels, sometimes you can have different filling ups, but the main thing is you generally follow the rule of the lowest first, and you fill up. So then you go back to 3s, then 3p, then 3d. Although honestly, this is where you start to get the exceptions to the rule. So this makes a periodic table, and this is what I got from a Nobel Prize winner who described it this way: how you make a periodic table from these 3 quantum numbers. Technically the 4, because if you double them, you deal with the 4. But remember, you have this cascading possibility where you have this triangle of possibilities. As you add quantum numbers, as you add energy, you have these exact possibilities, but nothing in between. This is what the 3D math forces you to do. And so we said the next one down would be 9. But if we have 1, 3, 5, 7 possibilities, and they must fill up in the way that we described, and there must be 2 electrons, and therefore 2 elements possible for each proton-electron combination, you have this going on. So if you count up 1, 3, 5, 7, and you double it, you get a pyramid like this. If you say they must fill up in this order, and you must fill up the 1s is here, then you must fill up the 2s, then you get to the 2p, then you have 3s, 3p, 3d, and then you stack them up like that, and then, by the way, you have the 4f down here, but there's no room for it, because who has room for that? And if you just move that over, the triangular structure, you stop to see it, but it's still there. You know, you're still stacking up in the same way, and you just reorganize it, and you move that guy over. Well, you have the shape of the periodic table. So the periodic table really is triangular. It's really a pyramid. It's just a kind of weird pyramid when you look at it. And so, you know, like the only difference is that, and if you look at the numbers, the rest of the triangle actually continues right here. It's just that we don't show it that way unless you have the way that I showed in my little display across from my office, where you actually see, oh yeah, you actually have this. It's just that you don't show it because it would make it too long. The pyramid would be too wide. So I want you to see this and see where this comes from, the fundamental quantum numbers, the fundamental physical properties, and that's true all the way through. This is another way of looking at it. This divides up the exact quantum numbers, but this is, you know, if L equals 0 and M equals 0, you have the S. If L equals 1, you have this. You have the possibilities of M sub L being like this. Oh, I was right. So it's the way the math works out. I actually had it right on the previous thing. I shouldn't have got myself. Then you have the D, you have 10 possibilities because you have 5 times 2. F is 14 across because it's 12. And you could say that if we were able to make protons that were gathered together enough to be big enough, then you would end up with that kind of thing going on. So the only way to expand the periodic table, you can't have negative protons. You can't have in-between protons. The only way to expand it, to have new elements, is to add protons. And the thing is, once you get to a certain point, you've got like 100 protons together in a small space. They don't like each other, they repel. And so it's hard to hold them together. They're inherently unstable. And actually, iron is the most stable nucleus, which is, I think, interesting because you'll see it's central to the story of the world from dust. It's also the most stable. And by the way, they have little things about, now they've named this, but they've been able, you have to try really hard to make new atoms because you have to have like more than 100 protons and you have to have more than that of neutrons because of the way that the physics works for that. Anyways, these are the ideas of possible, but you see that you have most of the dark line of stable isotopes is located down here, and then you have gray, and you have hardly anything stable once you get above 100 protons. So yeah, technically it's possible, but yeah, people are hoping that there's some extra stable arrangements out here, but I'm not sure if there are. The main point is the periodic table is based on counting numbers, and I want that to be, so if you actually knew wave math, and you knew the characteristics of the mass and charge, you would actually be able to calculate what the orbitals are. And you could actually, I wonder, this is one of the things why I don't think there's time travel, because it actually would be pretty easy for somebody who's had, not this class, but like the graduate school study in physics, to go back in time and actually calculate this out and to show people quantum mechanics. But we don't have any evidence of that, so I don't think you can travel back in time. You could figure out the periodic table using math and physics alone. The tiny star for this, there are some things we don't understand when you get bigger still. But for the simpler part, for the part of the periodic table that we use, we can actually see, you can't have a halfway orbital. You can mix orbitals, but you can't have something between S and P without mixing two that are already there. So that means the periodic table is a universal thing. And so then I want to just basically close this off with one last little thing to wrap it up.